Welcome to this course Measure Theoretic Probability 2. The course duration is 8 weeks. In this first lecture, I am going to talk about some introductory material and also mention some preliminaries. Without further delay, let us move on to the slides that have already been prepared. Note that, as I said, the course duration is 8 weeks and this course is actually a follow up from an earlier course which was titled Measure Theoretic Probability 1, and we are going to talk about the mathematical foundations of probability theory. In this course, our main focus shall be on sequences and series of random variables, and in short we are going to write them as RVs. We are going to focus mainly, as I said, on sequences and series, and in specific terms we are going to be interested in convergences of such series and sequences. In this course, familiarity with measure theoretic integration and other related important results such as the monotone convergence theorem, Fatou's lemma, the dominated convergence theorem will be important, and these are all essential prerequisites for this course. Now, for the convenience of the participants of this course, these essential prerequisites I will try to recall from time to time, but only in brief. It is recommended that whenever such prerequisites appear in certain lecture material, please go over and revise them from the reference materials that has been suggested. The lecture notes, as you see here, have been prepared using the following reference books, and I would suggest that you keep this material handy. The first one is the book by Robert B. Ashe titled Probability and Measure Theory. This book also has certain contributions from Catherine A. Doolyans-Dade. The second reference is the book by Kai-Lai Chung titled A Course in Probability Theory. The third reference is the book by Patrick Billingsley, and the book title is Probability and Measure. The fourth reference is the book by Rick Durrett, and the book title is Probability, Theory and Examples. And the fifth book is by Jean Jacquard and Philip Porter, and the book title is Probability Essentials. Most of the materials that will be discussed in this course will be based on the material from these books. So, again I will repeat that please keep this material handy with you. In addition to these reference books, there are several other points that you should be aware of as you are taking part in this course. The first thing is that the lecture notes have been arranged with numbered entries. This will be involving certain definitions, propositions, theorems, such things. And at the start of each week, the numbering will be reset to 1. That means the first result that you will see in week 2 will be numbered proposition 1 or lemma 1 or remark 1 or note 1, things like that, so that it is easier to refer to. Next important comment is that I would recommend highly that you actively participate in the Google group of the discussion forum. In addition to that, there might be certain live sessions being arranged, and in these live sessions we will be able to interact directly, and the exact schedule of this will be announced from time to time. In the lecture notes, in addition to the results that have been discussed and other comments, I have also included certain exercises which will be useful for the understanding of the material, and you are highly recommended that you try them out, and some of these may be discussed in weekly tutorial videos that will also be part of the course material, and discussion in Google group forum on these exercises and other problems are highly encouraged. Please note that each week there might be certain assignments which will be part of the final course evaluation. and it is also suggested that you try out problems from the reference books so that you get better ideas about the materials presented. And finally, this is a request that please do not send emails directly to the personal email accounts and communicate through the Google group discussion forum only. Now we move on to the main course materials and we start with certain preliminary results. These are primarily certain basic results which we will be using throughout the course, and this will also set up some of the very important notations. So let us start. So the first thing is to note that given any function capital X from a non-empty set omega to the real line. So this is a real valued function on the non-empty set omega, and if I choose any subset capital A of the real line. So given these two things, we can define something called the pre-image of this set under capital X, and this will be denoted by this symbol x inverse of A. So please be careful that the function need not be one to one or onto. So therefore the function capital X need not be bijective and need not have an inverse. This symbol you treat it as one generic symbol. So given any function capital X and any subset of the real line capital A, we are going to construct very specific thing called x inverse of A, and that is defined in this way. So this is a very specific subset of the domain set. So you are collecting points from the domain such that the range of the values falls inside the subset A that we have chosen. So that is exactly is the pre-image of that set. Now in this notational scheme, if we suppress this symbol small omega, essentially what we can do is that we can simplify this whole notation that is appearing on the right hand side and simply write this, so that our notation scheme becomes much simplified, and this is more of a shorthand notation that will be widely used throughout the course. So this again is an equivalent notation for the pre-image of the set A under the mapping X. Now we recall certain measured theoretic preliminaries. First thing to note is that we have the Borel sigma field denoted by B subscript r. This is generated by the open sets in the real line. Given a real valued random variable capital X defined on some probability space omega fp, we can now describe the induced probability measure which is denoted by P compose X inverse on the real line side together with the Borel sigma field. This is defined by this way, that given any subset coming from the Borel sigma field, we define P compose X inverse of A. So this will associate a number to this set capital A this way, that this is the probability supplied by the original probability space of the pre-image X inverse of A. Rewriting using the notation we have just discussed, this will be P of X in A. So this can be checked, describes a probability measure on the real line side, and this probability measure will be very important in our analysis. This is called the law or distribution of the random variable X. Now we can also describe the law of a random variable X by looking at its distribution function. In short, we will write capital D capital F as a shorthand notation. So this is denoted by capital F subscript capital X. This is a function defined on the real line and takes values between 0 and 1. This is defined by this way: you choose a real number X and assign the value, this value, to the point X. Here we are looking first at the left open right closed interval minus infinity to closed X and looking at the size that has been assigned by this probability measure we have just discussed. Remember, given this random variable capital X together with the underlying probability P, we have this law which is P compose X inverse, which is a probability measure on the real line side, and therefore, given this interval we can look at the corresponding size of it, and that is again rewritten by the definition as we have already discussed. This is the probability of the pre-image. Now, expanding this in terms of the definition, we can rewrite using this very simple inequality that the range of values of capital X should be less or equal to small x. Now, again the notation that we have just discussed, there we will get rid of this symbol small omega, and therefore, we will simplify our notation, and this reduces to more familiar symbol probability capital X less equals to x. That is what is the distribution function of capital X. So, all of these are equivalent expressions for distribution function of capital X. Now, this distribution function describes the law of a random variable uniquely. So, if you know the distribution function, you can uniquely recover in principle law of the random variable. Now, another point that will be very much important in our analysis is expectation of a random variable. This is given by this measure theoretic integration, which is the integration of the measurable function capital X with respect to this probability measure P. In expanded notations, this is exactly this. So, but most often we will use this shorthand notation to denote these measure theoretic integrations. Now, this expectation is defined by this integral provided it exists. So, given any random variable capital X, it might not be true that this integration exists. If it exists, then we will say that the expectation exists. Remember, this integration value could take values in the extended real line, meaning it could take values plus or minus infinity. We write E of x to denote this integration or the expectation. Using change of measure, this measure theoretic integration can be transferred to an integration over the real line, and therefore, the underlying probability measure, that was the P, now gets changed to the law of the random variable, which is now P compose x inverse. This is now an integration over the real line, but with respect to the law of the random variable. Note that the distribution function f x, which we just recalled, is a monotone increasing function. Therefore, we can also interpret this previous integration in terms of a Stieltjes integration, and this gives this very interesting interpretation for expected values of x, which is given by this Stieltjes integration with respect to the underlying distribution function. Now, in special cases, this above definition that we just recalled reduces to more familiar expressions. The first case is when x is a discrete random variable with probability mass function f x and support s x. In this case, the expected value essentially becomes a series over finite or countably infinite points small x, and it will sum up expressions of this form where small x denotes the value and this denotes the corresponding probability of taking that value. Here we of course require that the series should converge absolutely, otherwise we do not talk about expectations in these cases. If you are dealing with an absolutely continuous random variable, note that the underlying distribution of the random variable is given by a probability density function, which we again denote by this symbol f x, and here the expected value is given by this integration expression where the values are now multiplied by this function values and integrated against the whole range of the real line from minus infinity to plus infinity, but provided this integral exists absolute sense. If this happens, then we talk about the expectation. Now, as soon as we have recalled this notion of expectation, we can move on to more complicated expectations. For example, if you choose a real number p positive, then we can consider the pth moment, which is expected x to the power p of the random variable x, of course provided that it exists. If it exists, then we can get very nice inequalities involving these moments, and a major part of our discussion in this course will involve inequalities involving these moments. So, we go over some of the very important inequalities one by one. I highly recommend that you revise these materials from the reference book that has been supplied. The first important result is called the Holder's inequality. Here I state the versions involving random variables, but these statements can also be stated in terms of measurable functions. Let x and y be two random variables defined on the same probability space. Then for any two real numbers p and q between 1 and infinity such that they satisfy this relation 1 by p plus 1 by q is equal to 1, then we get this very interesting inequality, which is expected value of mod xy is dominated from above by this product, which is pth root of the pth absolute moment of x multiplied by qth root of the qth absolute moment of y. And this Holder's inequality actually leads us useful inequalities, some of these which we state in terms of corollaries. The first one is the Cauchy-Schwarz inequality. So, here what we need to do is to choose p and q to be exactly equal to 2, and in this case the previous inequality reduces to the Cauchy-Schwarz inequality. The second corollary involves a very nice bound of the covariance between the two random variables x and y in terms of the variances. He states that modulus of the covariances should be dominated from above by the square root of the product of the variances. The next important result involves property of the some kind of an increasing nature of these moments. Here what we are saying is that for any two numbers p and q, where p is less than q, then you look at the pth root of the pth absolute moment of x that is less or equal to the qth root of the qth absolute moment of x. So, this says that as p increases, then these values also increase, which is the pth root of the pth absolute moment of capital X. The next important result is called the Minkowski's inequality. Here we have two random variables x and y, again defined on the same probability space. Then for this specific range of p, where p is taken between 1 and infinity, we have that the pth root of the pth absolute moment of x plus y is dominated from above by this interesting addition, which is pth root of the pth absolute moment of x and again taken the pth root of pth absolute moment of y. The next important result is the Markov-Chebyshev inequalities. Note that the Markov's inequality is a very general inequality and special cases of that leads us to the Chebyshev's inequality. I have grouped them up so that it can be presented and digested better. So, to start off with, we take a random variable x and choose a positive real number epsilon. In practice, this epsilon is taken to be small. Then the probability that modulus of x exceeds epsilon, meaning that the values of x are either greater than epsilon or less than minus epsilon, that probability is dominated by in terms of the first absolute moment of x and divided by epsilon. More generally, you can take any p and write it in terms of the pth absolute moment of capital X. Here the same probability has been rewritten in terms of modulus of x to the p, and there you will end up with epsilon to the power p here, and applying the Markov's inequality you get this very useful upper bound. And for the cases when you choose p equals to 2 and after an appropriate manipulation, if you assume the second moment of x is finite and in particular the variance is also finite, then you get that away from the mean, the values of x from the mean by epsilon distance, that can be dominated by the variances with this scaling factor epsilon. This is a very useful Chebyshev's inequality. The final inequality that we are going to talk about today is called the Jensen's inequality. Let x be a random variable such that its first absolute moment is finite. Then for any convex function defined on the real line, so it is a real valued convex function on the real line with expected value of modulus of phi of x is finite, then you get this very interesting relation which is phi of expected value of x is less or equal to expected value of phi of x. In particular, you can see that we can choose the convex function x going to mod of x, and that inequality we have already seen earlier. These inequalities are part of something that will be very useful in our subsequent discussions, and as we go along the course we are going to see the usefulness of these inequalities. Okay. So, we are going to stop here today. We move on to the next lecture when we start discussing about the material from this course, and we are going to start off with something called LP spaces.